ustedes estén hoy aquí y que vayan a escuchar a los especialistas en este tema, en dar sus opiniones sobre qué acciones son las que podemos tomar individualmente para poder sumar este proyecto, sumar a esta solución. México aporta muy poca cantidad de emisiones en comparación con los grandes emisores a nivel mundial, pero pues cada quien tenemos que hacer nuestra parte. Muy buenos días y por ahora felicidades por este congreso.
Gracias, licenciado Daniel Arroyo. Pedimos, por favor, ahora al ingeniero Gabriel Navarro Guerrero nos diga un mensaje por parte de lo que es el municipio de Puebla.
Hola, muy buenos días a todos. Saludos a mis compañeros desde el presidio. Es un gusto estar aquí en la Benemérita de la Universidad Autónoma de Puebla. Para los investigadores y estudiantes que son de fuera, bienvenidos aquí al municipio, al estado de Puebla, a todos nuestros compañeros vecinos, pero sobre todo decirles también que estamos en una universidad de las más históricas del país, con más de 400 años de fundada y que ha hecho mucha investigación al respecto. Por ejemplo, nosotros como Ayuntamiento de Puebla tenemos un convenio con la UAP, con la universidad, para hacer todo el inventario de emisiones a la atmósfera del municipio de Puebla. Más o menos para que tengamos un contexto de este municipio, estamos hablando que circulan aproximadamente 500,000 vehículos diarios, ya sea públicos o privados, y bueno, el tema del transporte es un tema importante. Pero también, por ejemplo, como ayuntamiento y como municipio, estamos involucrados con Banco Mundial en un proyecto a nivel mundial que se llama Herramienta 3. Hay una herramienta que es una herramienta para toma de decisiones de eficiencia energética. Porque a fin de cuentas el tema de cambio climático es de acciones concretas y, como ya decía la delegada, ¿qué nos toca hacer a cada uno? ¿No? A veces hablamos del cambio climático como algo muy grande, obviamente es global, pero a fin de cuentas las acciones son individuales y específicas. En este caso de Puebla, somos de las 24 ciudades del mundo que Banco Mundial desde hace un año empieza con un trabajo de un día para poder, en rubros como agua potable, electrificación, edificación sustentable, transporte, poder compararnos con otras ciudades del mundo, pero sobre todo tener ejemplos prácticos de toma de decisiones en eficiencia energética. Y por ejemplo, ahorita que viene la temporada de lluvias, muchos hablamos de edificación sustentable, pero la verdad hay muy buenas prácticas y muy rápidas que se pueden hacer, e investigaciones muy precisas de cuánto cuesta, por ejemplo, que en las instalaciones de un gobierno municipal, por ejemplo, como el de Puebla, tener captación, tener el tema de generación de energía solar, pero sobre todo es, cuando hablamos con Banco Mundial y veíamos el caso de Puebla, que tenemos 100,000 puntos de luz en todo lo que es el municipio, y se van a transformar en energía LED, y con los puntos de luz otros 20,000, hablamos del tema de que aunque tú tengas eficiencia energética, por ejemplo, en el consumo, dice, oye, ¿y cuánto se va a ahorrar en la bolsa el ayuntamiento? Lo quiero poner como ejemplo porque yo siempre digo, si no es por ecología, hay que hacerlo por economía. No todos están convencidos del tema del medio ambiente. Digo, los que nos gusta el tema, estamos convencidos, pero hay otros, algunos empresarios que dicen, a mí, ¿qué ventaja competitiva me va a dar? Y hoy en día, en nuestro país, con el tema de eficiencia energética, nos coloca en una gran oportunidad para hacer acciones. Regresando al tema de Banco Mundial, cuando estuvimos en México y vimos el tema de eficiencia energética en alumbrado, nos decían, por ejemplo, para que se den una idea, todos los municipios del país pagamos en alumbrado una cuota fija, la más alta, y pagamos 12 horas día, no esté prendido, funcione o no funcione, sea horario de verano o no sea horario de verano, nosotros como ayuntamiento pagamos lo mismo. Entonces uno dice, cuando metes energía LED, cuando tratas de hacer alguna mejora, ¿dónde está el ahorro y el beneficio económico para poder seguir invirtiendo en prácticas verdes? Pues la respuesta es ninguno, siempre y cuando no tengamos medición. Y ahí es donde entra la innovación y ahí es donde entra la investigación. Si no medimos, por ejemplo, el consumo energético, difícilmente podemos ver, hagamos una mejora o una innovación energética, cuánto nos ahorramos, pero también en pesos y centavos no lo vamos a ver reflejado. Entonces, una de las estrategias que estamos viendo como Ayuntamiento de Puebla es empezar a medir algunos tramos segmentados de alumbrado, y también que las nuevas obras que vengan y los fraccionamientos ya tengan medidores para poder hablar con CFE y decir, oye, en realidad no consumo esto, he hecho mejoras de eficiencia energética y esta luz me queda más barata. Pero también hablando en el Palacio Municipal, que como ustedes saben, estamos en Puebla, en una ciudad patrimonio cultural de la humanidad, de las 10 que tenemos a nivel nacional, y además se crea ahorita la primera gerencia del centro histórico a nivel nacional, que ya estamos viendo prácticas verdes en el centro histórico. Le estamos metiendo al tema de buscar ya edificios que, si no bien son edificios históricos, que es complicado diseñarlos desde un punto de vista de edificio inteligente, pero sí de repente con algunas mejoras que nos hagan consumir menos energía. Y cuando hablamos esto con especialistas del Banco Mundial, pues está muy bien, podemos cuantificar el tema de energía, podemos cuantificar el tema de captación de agua pluvial, pero hay un tema importante, que eso no tiene que ver con la innovación, y tiene que ver, yo creo que el tema de medio ambiente, con la conciencia y con la voluntad. Es decir, si tú le dijeras a los 5,000 empleados del Ayuntamiento de Puebla que cuando no necesitan la luz la paguen, que cuando se vayan a comer apaguen su computadora, en fin, es un compromiso personal, realmente el ayuntamiento se ahorraría mucho en recursos. Entonces, el tema también de cambio climático, por supuesto que es un tema de educación ambiental, sino es un tema de voluntad. Pero aquí también exhortaría, por ejemplo, ahorita que ya estamos con la UAP haciendo nuestro inventario, también tratar de innovar y tratar de hacer investigación aplicada para el gobierno, ¿no? Lo hemos hablado muchas veces, yo vengo de la Universidad Autónoma de Chapingo, y también muchas veces cómo está desligado esta innovación, estos estudios que ustedes hacen con las prácticas de gobierno, porque a fin de cuentas el gobierno lo hacemos todos, a nosotros nos toca aplicar las políticas públicas, pero ustedes, entiendo que son investigadores y que son universitarios, les toca también aplicar estas buenas prácticas que bien necesitamos de manera urgente como gobierno aplicarlo. Entonces, no me resta más que darles la bienvenida a Puebla. Tenemos, para los que no son de aquí y vayan a visitar el centro histórico, tenemos las torres más altas de América Latina en la Catedral de Puebla, tenemos la primera biblioteca de América, que es la Biblioteca Palafoxiana, y en fin, tenemos muchos tesoros en la ciudad de Puebla que, por cierto, en estos 2 últimos años, Puebla ya es el primer destino turístico del país que no es de sol y playa. Y pues los invitamos, entiendo que aquí hay de Veracruz, de Tlaxcala y de otros estados vecinos, bienvenidos, disfruten la gastronomía de Puebla y sobre todo que sea muy útil este seminario de cambio climático, pero sobre todo que sea útil para todos. Y como les decía, bueno, nosotros como Ayuntamiento de Puebla estamos en la mejor disposición de trabajar con investigadores y que también el servicio social lo puedan hacer con nosotros. Muchos de ustedes están buscando una oportunidad laboral y también de servicio social, es decir, todo esto que estamos viendo en cambio climático, ¿en dónde lo aplico? ¿Cómo lo aplico en mi ciudad? Y dónde puedo ser útil, tanto laboralmente como mi investigación pueda ser aplicada. Entonces, como municipio de Puebla están las puertas abiertas, y nuevamente agradecer la oportunidad, agradecerte, Marco, también, que por cierto aquí Marco, que nos invitó, también está en el asesor en el tema de herramienta 3 con Banco Mundial, y también en este inventario de emisiones a la atmósfera, que seguro estoy, por supuesto que tener los datos iniciales de emisiones a la atmósfera es la primera base para tomar decisiones. Por ejemplo, el Ayuntamiento de Puebla tiene un programa de acción climática financiado por la Embajada Británica, en el cual tienen medidas de mitigación y de adaptación al cambio climático, y nos da un instrumento de corto, mediano y largo plazo de cómo actuar. Pero el Ayuntamiento, ni el gobierno federal, ni el gobierno estatal puede solo. El tema de cambio climático es un tema de todos. Muchas gracias y buenos días.
Finalmente, de esas autoridades que están aquí presentes, y les comento que nos sentimos honrados con que nos hayan acompañado, pero les reiteramos la invitación a que nos acompañen nuevamente a la conferencia magistral del doctor Luis Nestor. Gracias.
Muy buenos días. Tengo el gusto de presentar a ustedes al doctor Russell Snell, que desde el 2005 es director del Laboratorio de Investigación de la Tierra de la Administración Nacional para el Océano y la Atmósfera, o sea, la NOAA, de la División de Monitoreo Global en Boulder, Colorado. En 2011 obtuvo el premio NOAA por una trayectoria distinguida. En 2011 tuvo el premio Dan Albritton de la NOAA como destacado comunicador de la ciencia. Cabe destacar que el doctor Snell es autor de diversas publicaciones científicas y sobre todo en la revista Nature, una de las más prestigiadas del mundo, y tiene centenares de citas a nivel mundial por sus publicaciones académicas. Finalmente, el doctor Snell es además una de las personas que son autoridad a nivel mundial en el conocimiento de la variabilidad climática de nuestro planeta. Tenemos el gusto de recibirlo en este congreso con un aplauso.
Thank you very much. It is a pleasure to be in your beautiful city. My wife and I have visited many churches and art museums, and it's an incredibly beautiful city you have and historic. And thank you again for inviting us here. Today, we're going to learn, I hope, a little bit about climate change and what is driving it. It's a very simple process, and I'm going to show you something related to a globe that will help you to tell your friends about it. Okay, this is a globe. It's not even 1 meter across, but if I or you want to tell or show a student how thick the world's atmosphere is relative to this globe, I'm going to put my hand above the globe and above Mexico and bring it down. And I want you to say, stop, 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 when you think the top of the world's atmosphere is. Okay? Relative to this globe, if you were drawing a picture, how thick would the air be? It is as thick as one of my gray hair. That is hard to believe. When you fly in a jet airplane at 10,000 meters, 95% of all the Earth's air is beneath you. At 6,000 meters, half the world's air. There's very little air on the Earth. It's a very rare and precious resource. Now, if you look at the globe from this direction, what do you not see? Land. There is very little land in the southern hemisphere. It's all here in the north. And that's where people live. That's where vegetation grows. That's where we get our food. And that's where we put out our pollution. It's a very northern dominated system. And as you'll see on the data I show you today, it's controlled by what happens in really 3 places. North America, meaning United States mainly, Europe, and especially China, because the Chinese economy is growing very fast, and there are many, many people in China who want to have nice house, air conditioning, nice cars, so that is what they are doing. Now, I'm going to ask you another question. If you burn 1 liter of gasoline in your car, 1 liter, how many kilograms of carbon dioxide do you put into the air? There must be some chemists here who can tell me. 3. 1 liter produces 3 kilos of carbon dioxide. And that carbon dioxide goes into this very thin atmosphere. It doesn't go out to space. A lot of it, about half, goes into the ocean each year, but the other half stays in the atmosphere. So you can imagine all of the coal, oil, natural gas we are burning every day. Take that weight, multiply by 3. That's a lot of kilos of carbon dioxide. Why do we care? Carbon dioxide is a normal part of the atmosphere. Every breath we take, we put out carbon dioxide. It's important for a very simple reason. The atmosphere is what controls the world's temperature. It's very simple. Sunlight comes and it goes right through the atmosphere for the most part. It hits the ground or the ocean, and then it changes to long-wave radiation and comes up. The atmosphere is not heated by the sun from above, it's heated by the earth from below. And you are saying, that is not true. It cannot be true, but it is very simple. In summer, why do you go to a mountain to get cool? Or why is there snow on top of the mountain today? It is closer to the sun, it should be warmer. It's the other way around. If you want to get warm, you go to Veracruz, where it is lower. So the atmosphere, the heat comes up. But what holds the heat in the air is carbon dioxide, methane, and a few other molecules, but mainly carbon dioxide. And the carbon dioxide acts like a feather in a blanket. And when it's cold, you put a blanket on, and you are warm because the heat from your body is held by the blanket. If you put 2 thick blankets on, you will be warmer. And that is exactly what is happening in the atmosphere. Each carbon dioxide molecule we add is holding more heat. A little heat, but after you put many, many, many molecules, they collect and the heat will come. This heat at present is not staying in the atmosphere as much as many climate people had suggested, but it's going into the oceans. And the oceans hold 100 times more heat than the air. But eventually, as the oceans warm up, this heat will come back. So basically, you can argue in life about religion, politics, sociology, many other things, but you cannot argue against basic physics. Basic laws of physics cannot be discussed or changed. And the basic law of physics we are talking about is that the sunlight comes down, warms the earth, and comes up, and we are going to have climate change, warming. We cannot argue against that. We can discuss it, we can model it, but it's going to happen. If it isn't happening now, and it is, but it's going to happen a lot more in the future. And as Gabriela mentioned, we have a lot of people in the world, a lot of scientists agree totally that it's going to happen. What we don't know is how, where, and when. But what I'm going to show you today is the basic science that we have developed to show how the atmosphere of the world is changing. The air that you breathe now is very different in composition than what your grandparents breathed. And it's going to be a lot different for your grandchildren. And this is going to change many things. And one of them, as you probably have heard very much, is the ozone layer that has been depleted around Antarctica. And Dr. Molina predicted this many years before it happened, and he got a Nobel Prize for that. And it was a very good prediction, and we think that the climate change predictions that are being made are just as good. It's just that it's going to take a little longer to see. So let's start with some of the data that I'm going to talk to you about, and we'll go on to the first slide. I'm sorry, I don't have it turned on. Basic, okay. Now, this might be a little hard to see, but I think if you look closely, we'll be able to go through this. Every person on Earth, at least people who are eating healthy, use about 2,400 calories per day. But the average, and I'll say US person, in his lifestyle uses 240,000 calories. And these calories are for raising food, driving cars, heating houses, going to television, or watching television, running computers. It's a lot of energy. These are just in energy terms. And that's for food, many things, everything we use energy for. That's the same as having 100 people working for you day and night to help you live this energy life. So it's a lot of calories. And these calories come from where? Oil, coal, gas, maybe a bit of wood, and a little bit of solar, but basically it comes from these three energy sources here. Now, in North America, and I say North America, I mean more the US, because in Mexico you use less energy, but in Asia, they only use 25% as much energy per capita as the US, because the US wastes a lot, in the US and Canada. Mexico is not so bad. But this is something to keep in mind, that there's a lot of people in Asia, even though Asia only uses 25% as much energy, there are about 5 times as many people. So overall, they are using a lot of energy, and they're going to keep using it, and it's probably going to come from coal, oil, and gas. Now, the organization I work for has, we measure all around the world. If you want to measure how the atmosphere is changing, you can do it in 2 ways. You can put buildings all around the world and measure what is happening, but that is very expensive. Or you can collect air all around the world and bring it to a central facility. And our organization does it both ways. And these are just some of the buildings and locations we have. I just show you here because someday some of you students may come to work at one of these facilities, because we have to have people working here, and we have people from all over the world come at different times and work with us. This is our prime location in Hawaii, very nice location. It's at about 4,000 meters, 3,000 some meters, 3,500 meters above sea level. This is South Pole Antarctica, exactly on the South Pole. And the ice in Antarctica is 3,000 meters thick. Think of that. Ice 3,000 meters thick. And that's where the building is. And someday this ice may melt. When it does, there will be a lot of water on the Earth. We also have a station in Samoa, California. This is Barrow, Alaska. Summit, Greenland. This is not the full station. This is just one site. Again, the ice on this station is also 3,000 feet, 3,000 meters deep, a lot of ice. And we collect from around the world. I'm sorry, somehow we missed one picture. Right. It's a map of where we collect, but this is how we collect the air. See these bottles? We fill 2 bottles of air at different locations, at about 130 locations in the world. The air is collected and then it is sent for animal analysis in Colorado. And in one of these bottles, we can test up to 60 different species of gas. And these tanks, you see them here? Dozens and dozens of tanks. Those are calibration gases, because every measurement we do on one species, we do 2 calibrations. Because we have to know that the air that we are measuring today is the same and has the same validity and quality as it did 50 years ago when we began measuring. And when you students are in our lab measuring, or you're in the Mexican lab measuring, you'll have to be assured that your measurements are exactly calibrated to these, and that 100 years from now when we are measuring, we'll be able to say, in 2014, our data is the same. It's very important to have those measurements calibrated. Now, what are some of the results? This is the simple bottom line of what is happening in the atmosphere. This is years across here, and concentrations of CO2 going up. So time, many of you were born halfway through this. I was born over here somewhere. But this is carbon dioxide concentration. This is the average in the world measured from Hawaii. And see how it goes up and going up and up all the time. This is the CO2 that's collecting in the atmosphere. Why does it go up and down every year? That's very simple. Vegetation grows from only 2 things, water and carbon dioxide. And all of the vegetation in the spring in the northern hemisphere grows and sucks out the CO2 and makes the curve go down. Then in the fall, when vegetation stops growing, and it goes up, but see, each year it gets a little higher because of the pollution. So a little higher, down, a little higher, and it keeps going. So let's just look at this curve in the last 20, 30, 20 some years. There's the average, but this CO2, as I mentioned before, half of it is going into the oceans. So it goes into the oceans, and this is the measure of the CO2 concentration in the ocean. But when you add carbon dioxide and water, what do you get? Right, carbonic acid. You make an acid, and that acid is changing the pH of the oceans. So it's getting more acidic. When pH gets smaller, it means that there's more acid. So the acid in the ocean is starting to affect the plankton. So climate change has many, many different aspects. You burn CO2, it goes into the ocean, makes acid, and now the plankton, some of the small ones are losing their ability to make their shell. And eventually, there will be many species, including some baby clams and corals. They won't be able to make their skeletons, and the coral reefs will start dying. In some places they already are. In some places where they raise clams commercially, they cannot do it anymore because the babies die, because the CO2 is higher where they're doing it on land and in their tanks. So there are many other effects, but carbon dioxide is the most strong signal gas, and this is something that we have to consider how we are going to slow this down. Even if we stopped producing carbon dioxide today, absolutely stopped, we would still have the effects on the climate for 1 century, for 100 years. So everything we can do to slow this down now will help in the long term, but it is not an immediate fix. Now we're going to look at the carbon dioxide cycle from north to south over time. So this is the equator, and I'll need the person running the computer to put their cursor on here and press this. This is Mauna Loa, Hawaii. This is North Pole, and this is South Pole. Up here are the years. Watch the years. See how the CO2 concentration in the northern hemisphere, up and down, spring and fall, but it transmits down to the South Pole. But see, there's no real cycle in the south, but the CO2 mixes down and it grows, and it's growing and growing and growing. And as it grows, it holds more heat. So this will come up to about 2012 and stop, and then we'll start it again. Oh, 2013, 2014, oh good, I got a new one. But see, that's where we are today, the concentration. See how in the southern hemisphere, how well mixed the CO2 is? And then in the north, this peak is because of burning cars, putting out CO2 in winter, and it all occurs here where people live, around 30 to 40 to 50 north. Now let's do it again. It's very nice to watch this story. 1980, see, CO2 was only 340, and now it is up to 400, and it's growing. Up here, you see the different stations where the gases were measured, and you'll see we get more and more stations every year. And then eventually you'll see the Mexican station, which is very near here on Sierra Negra. You'll see it appear, and we'll talk more about that later. But this cycle is what's really driving the whole climate change. So keep in mind how the northern hemisphere is driving this whole equation. And this is an organization here in Mexico that is measuring this CO2, and we'll show you the data. And one of the principals, Carlos, is sitting in the audience. Stand up, and if you want to learn more and become involved, along with the university and other agencies to do the measurements, talk to him before he leaves today. This is the data from the Sierra Negra station. The years across the bottom, the same. Here's the years, and here's the concentration of carbon dioxide. Okay, here's when spring comes in, and the vegetation in the northern hemisphere sucks the CO2 out, and then vegetation shuts off, goes up, and then this is the middle of winter, or late winter, up, down, up, down, up, down. But see the trend line. When in 2009, very near Puebla, the average concentration was 385. Now look where it is. Now these red dots means that the data has come in and it's been analyzed, but it's going to be checked. Every data point here is checked over weeks and months of work to make sure that once it's a blue data, we're absolutely sure that this is absolutely the best we can do. The red data, it's probably 100% good, but we have to check and recheck the instruments and calibration, and then once we are assured. It takes a whole year to do one data point. Hard to believe, but we spend, because once that data point is out to the world, it will never be changed. This is another gas measured at the station, and you'll see here that this is SF6, or sulfur hexafluoride. It's a very powerful greenhouse gas. Right now it is in very small concentrations, but look how steadily it's going up. And sulfur hexafluoride comes from the leaky electrical transformers. In many countries, and I assume also Mexico, there are regulations now about controlling this. But in other countries, like India and China, where they are expanding electricity very fast, they are still using this gas. And this gas has a lifetime of thousands of years. So eventually this will become a very strong controller of greenhouse gases after we've fixed the CO2 problem. So even if we fix CO2 and methane, we'll still have these other gases. Now let's look at the three-dimensional picture. Remember the globe? We said there's not many people living in the southern hemisphere. Let's look here. Here's years across here. This is southern hemisphere. Here's the equator, northern hemisphere. So, and this is carbon dioxide concentration. So if we come up from the equator, it hits this graph right here. You come up straight up and then goes across. Look how much activity is in the north and nothing in the south. This is where people live in pollution. And this is from millions of measurements, millions and millions. And it includes the data in later years from the Mexican station here. But see, in this, the earth breathes once a year. It inhales in the spring, and then in the fall, see? Inhale, exhale, inhale, exhale. But each year, it gets higher and higher and higher. And this is what's driving climate change. What Mexico puts out is very small compared to India and US, but it mixes around. The air that you're breathing here today, probably a week ago or 2 weeks ago, came from China. And it mixes around the world. So what China puts up, what India puts up, what the US puts up, goes around the world. And I sometimes talk a little bit vulgar, but I will explain this to you in simple terms that you will probably remember. China, which puts out a huge amount of pollution, the air stagnates or holds. If any of you have been to Beijing or China, you can relate to what I'm telling you. So it's like having a big toilet for a house, and your family uses the toilet every day, but never flushes. So after 1 week, then you get a windstorm coming through China, and it's like flushing the toilet. Everything goes away, the air is clean, but what goes away comes to North America, it comes to US, and comes to Mexico within 5 to 6 days. So we all live in somebody else's sewer. So what we do here affects a bit locally, but what other people do upwind of us affects us much more. And it goes right around the world. So we are all in this together. Now, another gas that's very important in climate change is methane. Methane. This is concentration of methane in the atmosphere here, and this is the growth rate. For many years, the growth rate was 10 to 13 parts per million from the 80s until the 90s. Then it started going up very fast. And the growth rate, and it kind of leveled out, but here's growing up. And then it went down almost to zero and a little bit below zero, which is unbelievably big change. Sociologically and politically, what occurred in 1991 that could change the whole methane cycle in the world? Okay, let me ask you some other questions that will lead you to this. Which country, until very recently, produced the most oil? Not Saudi Arabia, not US. Russia. Hard to believe, big country, but yes. Which country, until very recently, till about 2 years ago, produced the most natural gas or methane? Russia. Russia. Isn't that amazing? And what did Russia do with it? They sent it to Europe, Western Europe. Western Europe lives on the gas. But what happened in 1991? Communism fell down in Russia, and they couldn't fix their pipelines as well as they used to, and the pipelines started leaking. And some of the holes in the pipeline were big enough to stick your head in, and they were losing huge amounts of methane. They figured it out. They got a loan from the World Bank, fixed the pipelines, made them all good. Methane in the whole world went down to zero. How do we know that? Because we can look at the isotopic composition of the methane. It has a signal in it. Every oil field has a different signature, a different oil, different gas, and you can see that in it. Then it went up and down, and then all of a sudden, in 1997, methane went up again. Boom! What happened in Russia in 1997? Do you remember? They had, their economy fell apart. The ruble was devalued by 10 in one day. So one day you were a rich person, you had $1,000 in the bank or 1,000 rubles. Next morning you had 10. They couldn't fix their pipelines, and they started leaking again. Eventually their economy got going. They fixed the pipelines, and it went down. So this methane is all due to man. Different processes. It's not all natural gas, but for the biggest part, it probably is. Then it went up a little peak and down, a little noise, and now it's kind of steady in here. So whatever we're doing, it's kind of steady. There's no big changes, but it could. But methane is very important because it's the second most important greenhouse gas, and also in the Arctic, all of the permafrost has huge amounts of methane. So if the Arctic warms up enough that the permafrost melts, this is going to, methane is going to start going up, possibly, really high. The curve to here, these may go up to here. If that happens, we're going to have, the world is watching this very closely. But look at the methane, how it looks in the northern hemisphere, in the world. Again, years across here, southern hemisphere, northern hemisphere, in concentration. So come up from the equator, boom, there. Look at the equator. South of the equator, nothing. All up here, where mankind is producing it, leaking it, da-da-da-da-da. And again, this comes from millions and millions of measurements taken around the world. Now let's put the three most important gases for climate change on one graph. This is years across here. This is going back. So this year 2014 is somewhere here. And then we go back 1,500 years, back 1,000, or the year 5. So year 500. Year 1,000, year 1,500, year 2,000. And you have the concentrations of carbon dioxide in red, methane in blue, and nitrous oxide. Nitrous oxide is a very powerful greenhouse gas here. And then you can see, going back 1,000 years, it was steady, and then all of a sudden here, the Industrial Revolution, it started going up. At least CO2 did, followed by methane, and then eventually nitrous oxide. Now you are asking yourself two questions. Number one, how can you know what the concentrations were 1,000 years ago? no measurements, no people. It's quite simple. When snow falls on mountains and makes glaciers, it captures the air that is concentrations at that time, because the snow has little bubbles in it. So one year you get a layer of snow, the next year another one, and it holds those bubbles in, and eventually, as the glaciers are formed, you have many layers, and you can, and it holds the air in little balls and little hollows. So you can go dig up a glacier, drill down, bring out the ice, pick a layer, you know what year it is, because you can count 1, 2, 3, 4, 5 back, because each layer is very clear. You melt the ice, and the air that was there at that time comes out. Very good. So you can look at the gases, and you can see that all of these gases started going up, but CO2 started going up with the Industrial Revolution. Then later on, when we started doing mining and drilling methane, nitrous oxide did not start until just very recently. And why is that? You all know the answer, but you don't know you know it. You've all heard about the Green Revolution, haven't you? And the Green Revolution is the result of better seeds, especially for rice, and fertilizer. And fertilizer has the methane in it, or ammonia. And when a plant takes fertilizer, it takes the ammonia and uses the energy from the hydrogen and produces nitrous oxide. So we have this nitrous oxide rapidly rising because of the fertilizer we're using. And I don't think we want to stop the Green Revolution, because fertilizers help crops so much. But see, it's going up and up and up. It came much later than methane and CO2, because we didn't really start using those fertilizers until very recently. But these gases, look how fast, over many, many years, the atmosphere was in balance, and all of these, everything is in balance here, and then all of a sudden, we're changing it. So eventually, no matter what we do, we have changed the atmosphere, and climate warming is coming. Now, another way to look at that is a graph like this. Years across the bottom. Pick the year you were born, or your parents were born. And this is the amount of extra heat that the atmosphere has collected from the gases. So look at the blue. This is carbon dioxide here, and I'll explain a little bit more. And then this is methane, and then this is nitrous oxide, NO2. These are the three big ones right now. And then there's other ones here, but let's just worry about these. So if we set an arbitrary number at 1, this is the greenhouse gas index. It's a measurement of how much extra heat the atmosphere is collecting from these gases. So if we just set 1990 arbitrary as 1, we go up to there and across, over time, between 1997 and the increase is this wedge here. So the number is 32, 1.32. It was 1 here, 1. We have added 32% more energy to the atmosphere since 1990 today, and that just keeps going up. Once that gets up to 50%, then there are a lot of models predict we're going to have really dramatic climate change. This heat is going into the oceans for the most part, but eventually it will go into the atmosphere and we'll have warming. We're already measuring warming if you look at the statistical averages, but it's not something that you can really feel in the air yet. This is a graph showing that if you set arbitrarily 0 at 1930s, just after the Great Depression, prior to that the air was cooler. From now on, and it's getting warmer. And each year there are records, but we're still only talking 1 degree Fahrenheit. That's what, 0.9 C. So it's not a lot of heat, but around the world and in the ocean, there's a lot of energy. So if this continues, which it will, and goes up here. Then once we get up here, where we have 2 and 3 degrees centigrade, it's going to be a very dramatic change. But right now, it's just starting. Now let's shift our thinking completely and look at something in the atmosphere that's a really good story, and it will make you feel good, because what I just told you shouldn't make you feel too good. The ozone hole that formed in Antarctica, which Molina got his Nobel Prize for, only forms around the Antarctic because of the way the winds flow in winter. And when the hole was discovered, there was 4 chemicals that were found to be the problem, and the world agreed in the Montreal Protocol to control these 4 chemicals: CFC11, methylchloroform, carbon tetra, CFC12. Montreal Protocol started in 1991. Let's look here. And these are measurements from the global network. The red is what's up high in the Arctic and high latitudes. The green is tropics, and then this is the south. You can see the concentrations. You all have to remember now that everything in the north is always much higher, and all of these gases and everything. But look what happened. In 1991, the Montreal Protocol went in. Countries agreed to start slowing down the production, not stopping it, but slowing it down, and then slowly phasing it out. Look here. This was 150 parts per million in 1991. By 2000, it's down to 40. That's a factor of 3. How amazing this is, that the countries would agree, they would obey, and the chemicals that were destroying the ozone layer would go down so fast. It's unbelievably good. Except CFC12. It didn't even hardly know the Montreal Protocol came in. Why is that? It's very simple. Again, you all know the answer. You just don't know you know it. How many new refrigerators have you or your parents bought in the last 5 years? Refrigerators last how long? 20 years? 30 years? Most people only buy 2 new refrigerators in their lifetime, maybe 3. So there's a huge reservoir of old refrigerators that are leaking and will be leaking for another 50 to 100 years. Where we live in Boulder, Colorado, it is a university town, and when the refrigerators get old, you sell them to students so that they can keep their beer in there. The refrigerators don't get cold enough to freeze, but they keep beer at just the right temperature. So there's many, many old refrigerators leaking the CFC12, but eventually it will come down. But we still have refrigeration and air conditioning, so those chemicals are in the atmosphere. So as soon as the production starts, they go up. Now, many of these have now been outlawed, especially 134A and 134B in the European Union. So let's look here. It was outlawed here, it started leveling off, and then it started up really fast. Now what happened here is that in some developing countries, they weren't restricted from using 141B, and also the people who made the regulations thought that there was no 141B made in China and India. And as soon as these countries found out that it was very valuable, they started producing a lot of it, and it went up. And this chemical is important in air conditioners on cars. So if your air conditioner loses 141B and you go to a garage, you have to buy a new air conditioner, very expensive. Or you can buy some of the chemical illegally and have it put in. It is more profitable to produce and sell 141B per gram than to make and sell cocaine. And nobody shoots you for making 141B, and you don't really go to jail. You just get a fine. So there's a very big market for this, but slowly the countries are now starting to realize, and this will come down. Now you'll notice here, there's no measurements. We knew this chemical was going to be produced, so we measured it in the atmosphere, and we found nothing, and then one day found a little bit, and then more. Because when you make a chemical, they always leak. Or if you put some in a car air conditioner, there's always a crash. Into the air goes the chemical. And this is measured in parts per trillion. Parts per trillion is a very small amount. To give you an illustration, if I take silver dollars, like Mexico used to have very big silver dollars, and stack them 2 meters high and make a wall 2 meters wide, and make that 250 kilometers. Think of that, how many silver coins there are. 2 meters by 2 meters by 250 kilometers. If you take one of those coins anywhere in there and scratch it, we will tell you, and this is an analogy, anywhere in that 250 kilometers, what meter and exactly what centimeter and what coin that is and what side you scratched it on. And we'll do that 99 times out of 100. That's the accuracy of a part per trillion. And all of the measurements in the world are measured the same way. They have the same standards. So any country measuring this using the WMO standards will do the same. We'll be able to measure it that accurately. Now this is a measure of the amount of ozone above the South Pole. Remember, the ozone hole was actually discovered in the 83s. Merlina and others said it was going to happen, but nobody knew it. And it was discovered here. And then we went back and looked at the data that we had collected for many years. And yes, the ozone was decreasing. It's just that we were not smart enough to know that it was doing that. But once the announcement was made here in 1983, you can see that we should have known this from the US data many years before, but we were just ignorant, or we thought the instruments were wrong or something. But once we started monitoring it, the rest of the world, you can see it went down, and around 2000 or so, the amount of ozone started going up. So the actual control of the CFCs is amazing, and it's effective, and it's saving the ozone. Why do we care about the ozone hole? Because if we hadn't have done what we did, the ozone hole would have got bigger and bigger and bigger, and soon it would start, if it didn't already affect people in Chile and Argentina, then it would get South Africa, and it would get bigger, and it would start coming to where a lot of people are. And the ozone protects UV light, so people would start getting more eye cancers and then skin cancers. And then in the oceans, the UV would kill the plankton, fisheries would have died. But amazingly, the world approached it, did the right thing, and it's getting fixed. I mean, it's an unbelievably good story. Now back to the bad story. China burns a lot of coal. And this is the world consumption of coal by region. And when this graph was made here in about 2012, you can see how much coal they were burning. And India and China are promising to give electricity to every house in China. And they're doing this by making one new coal burning power plant every week. So and coal burns very dirty. So you can see, even if we cut back completely on CO2 output, these two countries are going to still dominate with very poor sources. And we probably don't have any right to tell them to not do it, because we've been doing it for many years and using electricity and making electricity. So what happens in other countries is going to affect us. even if we try to control it. We should still try, but we've got to keep in mind what the truth and reality is. Now this is another interesting graph, again, years across here, and this is consumption of oil and natural gas put on one together. So you can see that for many years the US was doing most of it, but then look at what's happened to Asia. This is India, China, and the rest of Asia. They are now using more, and if they continue this trend line, can you imagine where it will go? And recently the price of oil and natural gas has gone down very fast in the last 6 months. So people are going to buy it as cheaper and use more probably instead of less. So this is what is happening. The forecast is that it will level out in the US, but really go up in the rest of the world. And Europe will hold its own. So eventually, these people, we hope, it will turn over. It's the same as it's done for Europe and the US. See how the US went up high, then came down, but unfortunately, going up now, come down. And Europe, the same way. But these are really continuing very fast. Now, one of the most dramatic manifestations of climate change is occurring in the Arctic. The Arctic ice floats on the ocean in the Arctic. It's not like Antarctic. You have just up in the Arctic, you have an ocean where the ice grows in the winter and then melts back in the summer. It's different in the Antarctic, where you have a continent. Underneath this, there's a country or a continent, and then the ice is sitting on top of land and growing thick. But as it melts back in the Arctic, I hit the button while I was talking. Here you can see the Arctic, and in 1980, just look at the outline of the ice. This is how much ice there was at the end of winter. By 2012, it had melted back each year, so there's only this much. And it's going down. This is the extent. See how fast the ice is melting? And eventually, if the ice melts completely, all of the polar bears that live on the ice to catch their seals will probably drown. And some models now predict that this will occur in the year 2030 to 2050. So in 15 years to 30 years, if this ice goes away, polar bears, for the most part, will disappear. But that will be a very strong indication that the oceans and the atmosphere are getting warmer. And remember, all of this permafrost that's up here, if it gets warm enough to melt, there'll be a lot of methane coming in the atmosphere. Now, when preparing for this talk, I tried to look up what the predictions were for Mexico. But in the time I had, the only graph that I could find that really showed at least part of Mexico was this one here. And this is the predicted change in precipitation. In climate change, it's not the temperature that's really going to change things much. It's what the temperature does. And it will change precipitation. And in this part of the world, this is northern part of, or North America and part of northern Mexico. Let's just look in winter. There's going to be a lot more precipitation in this part of the Arctic. And the scale here, the browns are much less, and the blues and greens are much more. But look here, in parts of Mexico in the winter, they predict, and this is when there's about 4 degrees C of heating, there's going to be a lot less precipitation. in Mexico in winter and spring, and spring is especially important for the crops. Summer is not going to be too bad in the north, but in fall. But if you take all of these together, and if these models are correct, the trend in the models is probably correct. The amount of decrease in precipitation will probably vary. But this is pretty scary that there's going to be this much drying up or this much less precipitation in Mexico. And when I go back, I will look up and try to find the maps for the rest, or you can go on to the internet and just look up IPCC Mexico predictions and get them for yourself. But if that is really true, which it probably is for the most part, it's going to get drier, and you can think of the stresses that will put on your country with less food, more need for water. Population will probably have to move from many of these areas. So it's something to keep in mind that could happen. Now, on a more local basis, there are people here who have set up a very interesting climate education center in Puebla. It's presently not operating, but inside this building, for many years, there was something called Science on a Sphere, and that was a big ball like this, I show you here, but much larger, where information is transmitted onto the globe. And Mexico is the world leader in putting in these institutions. A more recent one is this one here in Monterrey. This is a Science on a Sphere inside of an old iron foundry. And isn't that an amazing, beautiful facility? They've taken this 100-year-old iron foundry, and then this huge globe is hanging in the middle, and people can come around the side, and then you project all of the climate information and how the Earth is changing the weather on this. And there are at least 3 or 4 people in this audience, including the organizers of this meeting, that are very knowledgeable about these sciences on a sphere. So please talk to them and to the other people that are here. And would all of the people who are involved in climate on a sphere, including our host Maria, raise their hands or stand up? Maria, stand up. Science on a Sphere, and Carlos, stand up, and great, and the other, raise your hand. Don't be shy. These people are Science on a Sphere, and talk to them because it's an amazing facility. And Mexico, as I say, has more than any other country on Earth. And one other unique facility in this area is the observatory that's being built on Sierra Negra. This is the building and the platform here. It's up and running. The instruments have not been put in yet. They'll be put in next year. So Puebla will have one of the observatories, one of the probably 10 in the world for real-time monitoring of the climate. I think we'll finish now and be open for any questions or comments you might have. I think this is a good time. I thank you very much for your attention, and I hope you as students will be able to use the data from the observatories in Mexico here and other observatories. If you want to look at the data that NOAA makes, it's freely available.